Hi everyone, in this video I will be solving two RC circuit problems using the Prada computational thinking framework, and then I will be supporting my solutions with simulation in Volstead. So the first question is a B-level question, and the next one is a challenging problem from Randall. Both are from Randall. So let's have a look at the first question. We need to find tau for the discharge of the capacitors. We have two capacitors which are in parallel, and then we have two resistors which are also in parallel. Let's start by decomposing the problem first. So first I will break the problem into three steps. Into three steps. First, finding the equivalent capacitance, and then equivalent resistance, and then finding tau. And for abstraction, I ignore everything except the component values and how they are connected. I don't need to worry about initial charge or voltage here, only the structure of the circuit matters for finding tau. So in abstraction, we will be focusing on essentials. In pattern recognition, we need to recognize some patterns, okay? So here I recognize that both capacitors are in parallel and both resistors are in parallel. I know the rule, so capacitors in parallel are directly, while the resistors, as we see here, they use the reciprocal formula. And then we have finally our algorithm design. Now in algorithm design we will be applying the solution. Okay, so let's start. For finding equivalent capacitance which are in parallel, we will be adding them directly. 2 microfarad plus 2 microfarad gives us 4 microfarad. So let me first write the formula for parallel. C1 plus C2, and it goes on. And for resistance equivalent in parallel, we need to find the reciprocals. Okay, so R wait wait 1 over R equivalent gives us 1 over R1 plus 1 over R2, and it goes on. Our equivalent resistance is R1, R2, R1 plus R2, 1 kilo ohm plus 1 kilo ohm, go on the key, 1, oh here we have multiplication, 1 kilo ohm plus 1 kilo ohm, go away, and then we have 500 ohms. So here we have the we finished phase 1 and then phase 2, and then we will go on to phase 3, which is finding tau. The formula for finding tau is R equivalent multiplied by capacitance equivalent. $500 ohms multiply by 4 microfarad. This gives us 2 multiplied by 10 minus 3, which is 2 microseconds. So we found the tau, which is 2 microseconds. Oh my god, I wrote here 2 microseconds. Okay, so let's move on to the next question. Question number 81. So the circuit has a 10-volt battery, and then 60 ohm resistor, and then 40 ohm resistor, and a 10 ohm resistor, and a 2 microfarad capacitor. There are two parts in this question. First, A, finding the charge at steady state, and B, finding the time for the charge to drop to 10%. Let's use our states for using Prada. First one was what? Let me copy this, duplicate, and move it down. Oh my god. I can duplicate a text I see. Okay, let's just move to stage 1, which is decomposition. So I decompose this into 2 separate phases, as we said before. Phase 1, the switch has been closed for a very long time. I need to find the charge on the capacitor. Charge on the capacitor. And phase 2, the switch then opens at t equals 0. So I need to find when the charge drops to 10% of its initial value. In both cases, we need to find charge. So next stage, we have abstraction. So for phase 1, the key abstraction is the steady state condition. After a very long time, the capacitor is fully charged and no current flows through it. This means I can treat the capacitor and the 10 ohm. Here we see the 10 ohm. This 10 ohm. So I can treat this capacitor and 10 ohm as an open circuit and remove them. I can just remove them. Yes, so, and then this circuit simplifies to just the battery with 60 ohms and then 40 ohms in series. So we finished abstraction. This was abstraction. Third, we have pattern recognition. So in pattern recognition, I can recognize that the same pattern from problem 1. To find tau, I need to identify the equivalent resistance and the capacitance of the discharge, exactly like I did in question 1. The key difference here is the first I need to figure out which resistors remain in discharge after the switch opens. So the 60 ohm resistor is disconnected with the switch. So only the 10 ohm and 40 ohm resistors remain. We finish this part and then we have algorithm design. finally we can solve this question. So let's start solving this question. Step 1. We need to simplify the circuit to battery 60 ohm and 40 ohms in series. So no current flows in here. So we need to find the current. I equals to 100 volt over 60 plus 40 ohms. 100 over 100 gives us 1 ampere. So we found the current, and now we need to find the voltage. Step 2. The voltage across capacitor equals voltage across 40 ohm because they are parallel. So voltage in capacitor equals to I multiplied by 40. This gives us 1 ampere multiplied by 40 ohm, which is 40 volts. So our capacitor has 40 volt while it is closed. And now we can find charge. Initial charge. We can now find initial charge. The formula is QO equals to E times comandaki C. Yes, so our voltage was 40 voltage multiplied by 2 microfarads, right? 2 microfarads. 2 multiplied by 10 minus 6 farads. This gives us 80 micro charges. Okay. Microcoulomb. Okay. So we found the initial charge. Let me highlight this. And now we are moving to part B. So once 60 ohm is cut off, then we will be having 40 ohm and 10 ohm still connected to the capacitor. Now 60 ohm does not get any charge, but 40 ohm and 10 ohm resistors are connected to the capacitor. So let's solve resistance equivalent first. Or 10 plus 40 ohm gives us 50 ohm. We are adding them because they're in series. Okay, so this switch is open and the battery is disconnected from the capacitor. And now the capacitor has only two resistances, 10 ohm and 40 ohm in series. Now we will be finding the charge. So the formula is Q equals to Q initial minus T over RC. RC here is tau. So our Q is 0.10% gives us 0.10 multiplied by Q equals Q initial E minus tau over 50 ohm multiplied multiply, oh my god, 50 or multiply 2 microfarads. This equals to ln 0.10 minus over 2.0 microfarads. So time equals to minus 50 multiplied by 2 microfarads ln 0.10 equals to 0.23 microseconds. I'm highlighting this answer that we got here. So we successfully find both parts. Now let me show this in full study simulation of this question. So in the simulation we did everything, we connected everything just like in the question. In the simulation you can see when I close this and I click capacitor, I can see here it shows that 40, it is now 40 voltage. It has 40 voltage. But when I just open this and I click capacitor again, this is 0 volt now. So the capacitor discharging after the switch opens, our capacitor is now discharging after the switch opens from 0 volts to, from 40 volts to 0 volts. So to summarize, the key pattern across both problems was the same. First we identified the discharge loop, and then finding the equivalent resistance and then equivalent capacitance, and then we calculated the tau, and then we applied the exponential decay equation. So using product computational thinking framework helped me to decompose complex problems into clear manageable steps, and the full-set simulation visually confirmed our mathematical results. So that's it. Thank you. Goodbye.